Thank you. So yesterday I introduced two types of units, bus units, bicyclic units. I showed that the bicyclic units, if they are not trivial, then give you an element of infinite order. You can prove, it's in the notes, that the bus units, most of them are also of infinite order. So except for some exceptional cases, bus units and bicyclic units are of infinite order. Now, using this fact, you can prove the following theorem, which is an old theorem of Higman. That tells you that sometimes you have very few units, and it shows that the sometimes is almost never. And so it says the following. The following are equivalent. The unit group of grouping of a finite group is finite. Secondly, the trivial units, of course, this is obvious, is finite. The augmented units are finite. And thirdly, you describe exactly the groups for which this happens. G is abelian of exponent a divisor of 4 or 6, or G is the quaternion group of order 8, direct product with copies of the cyclic group of order 2. So these are the only cases. It shows you almost never. And it's a very good exercise, maybe you should try this, to prove this result making use of those units. We've shown that there exist bicyclic units if there are cyclic subgroups that are not normal. And if you have non-trivial bicyclic units, you get infinitely many units. So because of that, you prove that every subgroup has to be normal. These bus units are then basically used to get rid of large cyclic subgroups. You have to go to divisors 4 or 6. So you should try to prove this. So almost all the time there is an infinite group. Yesterday I also gave an indication that sometimes free groups are there. Now let me show you, or try to indicate you, that there is almost always a free group in the unit group. And I'll do this as follows. In that context, it's good to make use of a theorem of Salwa. Maybe he hasn't explained it exactly like this, but let me dedicate it to him at least. So R is a torsion-free ring. By that I mean the only additive torsion is the 0 element, so characteristic 0, for example. You take two elements A and B in R that are nilpotent of degree 2. So think of the bicyclic units, 1 plus an element of square 2. Then the group generated by the unipotents, 1 plus A and 1 plus B, is free of rank 2. If and only if either AB is transcendental or AB is algebraic, and you need the following condition. And the condition says the following: one of the eigenvalues of AB. To talk about eigenvalues, I use the regular representation in the algebra, and then I compute eigenvalues. One of the eigenvalues, lambda of AB, is to be a free point. And by a free point, I mean that this group is a free group. Remember this yesterday was introduced as 1 plus lambda E21. It comes down to computing eigenvalues. Let me give you a little indication of the proof. Okay. So basically everything is calculated here in the ring generated by A and B. So let me look at this ring, A and B, which is a subring of R. And I could do the same thing if I tensor up with Q, I could work in QAB. Okay? And no, it's not commutative. If it's commutative, then there would be nothing to do. You would not find a free group. What was I going to say? So I work there. Let me call this the algebra A. And you can easily show that the elements here are in the ring generated by A, and then you have B, Q, A, plus Q, A, B, plus A, Q, B, A. So it's in some sense a four-dimensional module over QA. You look at the radical of this ring, you prove it's nilpotent. Okay, and then you prove that 1 plus A, 1 plus B is free, even only if you look at its image in this ring, this has to be free. It's an easy exercise because the radical is nilpotent. Okay, and then this is the important stuff. You would like to describe this a bit. This you can show is a direct sum of copies of Q plus, and this is very relevant, 2 by 2 matrices over extensions of Q. The degree 2 is really relevant that you get this here. You might say that you have n copies. Okay. And the use here, this set is equal to the set of, what will I say, the non-zero eigenvalues of, if you look at the regular representation, rho of AB. Now here, this is what I forgot to mention. I assume here that AB is algebraic. Otherwise, this would not be correct. Well, you can do this, but for the calculations here, then that is algebraic, that they get finite dimension. Over Q, yeah. The reason why I restrict to algebraic, because I work in the groupings of finite groups and everything over Q is algebraic. Okay, but this is relevant. And then you can also show that this 1 plus A, 1 plus B is free, even only if there exists an I, so that 1 plus E121 and 1 plus E21 lambda I, or Ui, is free. Requires a little proof. And such a mu I is called a free point. And from that, the result follows then. But the nice thing is really that you get only degree 2 representations. You get to these things, and then you get to groups that I mentioned yesterday in the context of Sanov's results. Sanov gives you 2 by 2 matrices that give you something free. Okay. There might be many copies of Q. Okay. Now, using this result and a little bit more, Marciniak and Segal they proved that if you have a non-trivial bicyclic unit, if U is a non-trivial bicyclic unit, then, and by the way, non-trivial means in this case different from 1, and this always exists if there exists a cyclic subgroup that is not normal. So if not all subgroups are normal, this always exists. Then they proved that this bicyclic unit, together with its involutive one, the involution I used yesterday, so if this one is 1 plus 1 minus g h g hat, then this one is 1 plus g hat h inverse 1 minus g inverse. Well, this is a free group. So for all groups, except those groups which are very special with all subgroups normal, you always have a free group of rank 2. So it means the unit group is large. I mean, fascinating to me is, the nice thing is you really have a constructive proof of a free group. You show it. This result was a very long time ago already known that there exist free groups. This is an old result, but non-constructive. The proofs, even in the constructive way, are definitely not more complicated than before. So it took about 30 years of research before people actually showed this, which is a bit funny. Probably nobody thought about it before. Okay, so what have we done? We've introduced the unit group. We said it was relevant. We proved that the unit group is in general very large. And then would now like to describe better the unit group. Now, I always indicated before examples such as the ring of integers ZC and 2 by 2 matrices over something. So somehow I always go to ring of integers in number fields or to matrices. This can be done in general in group rings by the Weddertion Artin theorem. So let me come to that now. This is section 3, the Weddertion Artin theorem. Okay. So let me recall you if a ring R is a semisimple ring. I came recently from a conference where not everything was associative. For me, everything is associative and is an identity element, right? So R is a semi-simple ring, if and only if R is the direct product of matrices over skew fields. And I is positive integers. Okay. Then, if I apply this to group rings, so if I take G a finite group, you can do it, and I take the rational group algebra, I could use another coefficient ring, then you prove that this is semi-simple. This is an old result of Maschke. Hence, you know this is the direct product of matrices over skew fields. And all the rational representations are included in this ring. So all your information somehow is there. But I'm not interested in this ring, I'm interested in ZG. But the thing is, even if I give you QG as matrices, and I just give you this and said this is a group ring, where is the integral group ring? Where is it? This is a major issue. Okay? But even if I tell you theoretically QG is of this form, fantastic, decompose me this concretely. Find these matrices, find these DIs, find these degrees. Good luck. Okay? But why would I want to do that? If I can describe this ring as matrices, basically I'm now back into linear algebra. And linear algebra, we think we know it. It's not always true, but I would like to reduce this. So I would like concretely to describe this decomposition and get a real isomorphism from group ring elements to matrices. Okay? To do that, first of all, I have to know how many components there are. How many primitive central idempotents are there? So if I look at the primitive central idempotents, call them E1 and EK, I would at least like to describe those also. If I describe those, then I have somehow located the simple blocks. Now I want to describe the simple blocks concretely, so that I can say, if I take a matrix, it looks as a group ring element this way, in the hope to rediscover this. To describe matrices, you would have to discover elementary matrices. So I'm looking for elements, say that if EI is a primitive central idempotent, and I know it's a matrixing or a division ring, first thing I have to do, I have to look for elementary matrices. What are elementary matrices? Well, these are things that satisfy this formula. And the sum of the EIs is 1. So I want to find these elements concretely. And then everything is reduced to linear algebra, and I can put it in a machine. You find a slave who does it for you. For example, Leo Margolis will then do it for you. Okay, so this is the project. Discover the primitive central idempotents, discover these idempotents, and decompose this. And then you're set. That doesn't mean everything is solved, but at least you can start playing. Okay. So first of all, to do that, I have to describe primitive central idempotents. I told you yesterday the hats of groups are idempotents. This is the only construction I basically know. So I hope for the best I manipulate this a bit to find other idempotents. In general, if I take a hat of a group, this is not central. It's only central if it's normal. Okay, but it's not central yet. So therefore, I introduce the following notation. So let G be a finite group. And a normal subgroup of G. And I'm going to define a new idempotent, which I denote this way. It's by definition G hat if G is equal to N. And otherwise, it's the product of differences of hats, N hat minus D hat, where D hat is such that D over N is an element of the minimal subgroups of G over N. The minimal non-trivial normal subgroups. Of G over N, and of course I assume D contains N here. Okay? Exercise proof this is an idempotent. Okay? Okay. Well, maybe as an indication that they are relevant, if G is abelian, then these are precisely the primitive central idempotents. If I assume something on N, then the EGN are the primitive central idempotents. Of course, central is irrelevant here. And here, N is a subgroup of G with G over N cyclic. Now the cyclic is very easy to see why it has to be cyclic. Why? Yeah, this should be absolute. Why it has to be cyclic? If I look at the rational Wedderburn decomposition of QG, it's a direct sum of matrices over skew fields, but it's commutative. So the degrees are 1, and the skew fields are fields. So it's a direct sum. I'll write it this way, EIs, but these are fields. And as an algebra, this is not the group algebra of GI, this is the QG times EI, but as an algebra over Q, it's generated by this group. This is a group. But this is a group living in a field. And subgroups of fields are cyclic. So by the isomorphism theorem, this is G over some n. So the G over n has to be cyclic. That's why the cyclic is there. Okay, so basically these GIs are the kernels of the linear characters for this group. Okay. So in the commutative case, I know all the primitive centerlized idempotents. Also, this is also old stuff in some sense. And you can then also show, if you want, that this thing is isomorphic with Q, C, a primitive root of unity of order this group. Okay. This is a very old result of Perlis and Walker, I think. Okay. Now, you might think, if we have listened to all kinds of lectures on representation theory, you might think, well, instead of doing that, I work ZG in QG, I work in CG, it's also semisimple Artinian, and we know formulas for the primitive centerlized idempotents here. They are known using characters. Okay. I'm not going to write it down, but using the characters, you know them. Because it's a matter of flavor. You say you know the characters, so you know the primitive centerlized idempotents in CG. But I would like to write them really, the information that I get from the idempotents, I would also like to describe the matrices. It's not enough information, it seems, there. But on the other hand, even if I know the primitive centerlized idempotents here, with some Galois descent, I should be able to get them here. But this doesn't maybe give nice formulas internally in terms of the group. That's the only information I have. Okay, so I have to do other things. So in general, we don't know. But for large classes of groups, we know. And this is what I want to explain. So now I need some notation. So that for some class of groups, I can execute this project here. And this is implemented in the program Wedderga of GAP. So if you have a slave who can program it for you, they do it and it spits it out. Then you have to be able to read it, and then your slave tells it back to you. This is what it is. This is the way I operate with Leo and Andreas. I abuse them a lot. But thank you for that. Okay, so here is a proposition. So let G be a finite group. H and K subgroups. Such that, and I assume that K is the smaller one of the two. So this is data. Then, if I denote by lin HK, the following set, it's the linear characters linear character on H with kernel K. They might not exist, but this will be non-empty. This is easy to prove. if and only if the following two conditions are satisfied. The first one I wrote S1. It means that K is normal in H. It's the kernel of something, so it has to be normal. And secondly, it has to be a linear character. If that's the kernel, then H over K should be cyclic. That's easy, right? Now, what is more important is, if I induce the character chi to a character of the group, so if I assume chi is such a character, then the induced character is absolutely deducible. If and only if the pair HK satisfies the third condition, which is called S3. And what's the third condition? For every G that is not in H, there must exist an H in H such that the commutator AG lives in H but not in K. So the induced character is absolutely irreducible even only if these strings are satisfied. So if a pair satisfies these conditions, then the pair is called a Shoda pair. Dedicated to Shoda, who proved things on this matter. Okay. Now, this was used by Olivieri, Del Rio, and Simon to prove the following beautiful theorem. Spanish writes so many accents and I never know where they are, but here it is. Okay. Of H and G, yes. Yes. So assume that I have a character chi that satisfies all this. Okay? Well, then there exists a unique idempotent, unique primitive central idempotent E such that the character computed at E is not equal to 0. So I assume that this chi satisfies these properties. So chi is the representation associated with this. So I have a Shoda pair, therefore I have a linear character chi. I assume this is the chi that also satisfies this property. Okay? I forgot to mention something. No. Yeah. Well then, and this idempotent will be denoted E, I remember well, Q chi. I think this is the notation you used. We denote that idempotent this way. Furthermore, and this is the important thing, one can describe this thing. It is the sum of all the conjugates of this idempotent. I always get the So read this as the sum of all the conjugates of this idempotent. of this one. It's a rational thing, yes. But I'm not saying this is equal yet, I have to add something here. So this thing you can choose as a transversal of the centralizer of this idempotent in the group. But in the first instance, it's the sum of all the idempotents. Now, it's not equal to, there is a rational multiple there. So there is a Q here, and you can describe it. Okay. Some quotient of indices of some subgroups. It's not relevant at the moment. All right. Now be careful. If you would know that these conjugates, there will be again, of course, idempotents. The conjugate of an idempotent is an idempotent. If these conjugates would be orthogonal, products are zero, then this is an idempotent. And it will be central because it's the sum of all the conjugates, right? But in general, they're not idempotent, they're not orthogonal. But it's almost an idempotent. Right? So these sums is almost an idempotent. There's a scalar missing. Okay? D is defined, it's used to define the epsilon hk. Epsilon hk is a product of differences of hats. So here is where you refer to the D. So there's two steps. You first define epsilon kh, and then you define the E. Okay? And this thing we will give a name. This is usually denoted by E, G, H, K. So if H and K are a Shoda pair in a group G, then this is the definition of EGHK. And the EGHK is an almost idempotent. Okay. Now, not all characters of a group are induced from a linear character. If there were, then we have written something very general here. Okay? So therefore, we introduce a name. We say a character is monomial. A character from a group G is monomial if it's afforded by a representation coming from a linear representation. So if it is an induced representation or character from a linear one. And a group is monomial if all characters look like this. Okay. Hence, if we were in groups of this type, then we can apply this always. Because every character, irreducible character, looks like this. Okay, that's good news. Now, okay, we know for a large class, and I'll come back later to what large really means here. We now have a description of idempotents, primitive central idempotents, but I have not said anything about how the matrices look like. So that's what I have to do now. But to do that, I need more assumptions. By the way, there are several experts in this audience who've worked on this and who've described Shoda pairs and described how many Shoda pairs you need for special classes of groups, for example, metabelian groups, polycyclic, metacyclic groups. So some of them sit here, you can talk to them. They know more than me probably about this. Okay, so now I need an extra definition, and these things will be used in the tutorials, I think. Okay. So let me write down that as a proposition. So G is a finite group. H and K are subgroups. K is the smaller one of the two. then the following are equivalent. First of all, HK is a Shoda pair. And the different conjugates of the epsilons are orthogonal. Orthogonal mean that product is zero. So this is a situation that each of these, if I take distinct these, then these two things will be orthogonal. That means this sum is an idempotent, and it's obviously central. That's equivalent with HK. I'll introduce the terminology, is a strong Shoda pair. Added the word strong, and this means the following. So here is the definition of strong Shoda pair. It's probably not appropriate to call anything SS, but I'll do it anyway. H is normal in the normalizer of K and G. H over K is cyclic. And maximal abelian subgroup of this quotient. And thirdly, this we know, well, more or less for every G in G, if G is in the group but not in the normalizer of K, then epsilon HK is orthogonal to epsilon HK conjugate by G. Which tells you basically the normalizer is exactly the centralizer of the epsilon HK. Okay? There is a third one which is in the notes here, which I leave you to read. So now we have strong Shoda pairs. Now let me first of all, and then let me say a finite group is strongly monomial. Finite group is strongly monomial if every irreducible character of G is strongly monomial. By that I mean it's induced from a character which gives related to two subgroups that satisfy those conditions. So it's basically the groups where you can apply this. Okay, again, a beautiful result. And as I said yesterday, if you say anything, if this, then blah, blah, I want to know that at least the if is a reasonable class. And this is the theorem. Probably to dedicate to the same people. I forgot who proved this. You remember, Uncle? Strongly, the abelian by supersolver are strongly monomial. You and these two other people. So the same people proved that every abelian by supersolvable group is strongly monomial. You know what abelian by something means? It means you have a normal subgroup N that has this property, and G over N is supersolvable. Okay? So it's a large class of groups, at least. It's an interesting class of groups. Okay. Now, in case of meta-abelian groups or meta-cyclic groups, you can make life a bit easier. It's in the notes. But I want to come to the fact, if you're in this situation, in some sense, I can describe the Wedderburn decomposition. Okay, so this is a theorem. Probably again by the same people. And it says the following. So you have a strong Shoda pair, HK. In the group G. Chi is the linear character in HK that exists. Now we know. I take N, the normalizer in G of K. I take the index of G in N, I call this little n. Then we have the index of H in K, I call this H. And the group HK we know here is cyclic. So I choose a generator, and let's say it's the coset of X. By X bar, denote the coset. Okay, with all this data, one can then prove the following. First of all, and this was indicated in the previous, N is exactly the centralizer in G of this epsilon HK. This we already know from the beginning. 2, the unique idempotent on which chi is not 0. That's the unique idempotent of QG on which this character is not 0, is exactly EGHK. Okay, somehow we know this from before. And now I have to see what I'll do. I'll write part of the result here. I want now to describe Q, G, E, Q, high G. So this simple component. Right? This is a simple component. In this fantastic book you all bought yesterday, this is denoted this way. Q, G, H. Right? Just notation. Now what is this? Now look at the degrees. This is an n by n matrix ring over a crossed product. And what's the cross product? It's Q, you add a root of unity of order H, primitive root of unity of this order. The order of the cyclic group. Then you have a cross product, so star, and then you have N over H. You know cross products or not? My good friend Pasman once gave a lecture about cross products, and there was a general audience, and he said, I will talk about cross products, and I'll give you not the definition, everything is in the star. And he didn't define it. So what is this? This looks like a group ring. You could think of as a set, the group ring of this group over that field. But the multiplication is a bit more complicated. If I multiply 2 elements here, I get again an element here times a scalar there. And if I'm in a group ring, I can switch group elements and ring elements. Well, if I switch a ring element over a group element, it becomes some automorphic image of this ring element. And you can prove that this is a Galois group, and that this Galois group acts on this field in this use. And it's in detail explained here. Okay, so you might think we're done. I've described these are matrices. Very nice, but this star is a complication. First question is, when is this a division algebra? It's not obvious. It might maybe be again a matrix ring. So in some sense we've described things, but we're not done yet. But at least we have done some reduction, and it's for some nice groups, this will be something nice. I'm not finished now, right, if I want to do this, because at least I described somehow where the matrices are. Maybe if this is a division ring, I know the degrees of these matrices. But I want to explicitly describe this as a matrix ring. I want to find elementary matrix units. I don't know. For some classes of groups we know, if I remember well, we did this for nilpotent groups. Maybe under some mild restriction, I don't remember, with Van Gelder and Del Rio, maybe Olteano. But I'm not going to write this down, this would be too many formulas. But for some classes of groups, and nilpotent groups are almost abelian groups, right? One can do a lot, like execute this program. And then you get complete control on this decomposition. Okay. Now in WeatherGA, they have implemented this stuff. So you first have to learn the language how to implement. Leo will explain you this, maybe. And then WeatherGA spits out this decomposition, but you have to be able to read this. As somebody who doesn't know GAP, or hardly know GAP, I would like that GAP shows me exactly this formula, but they don't. So somebody should make a nice interface so that for dummies like me, one can read this stuff also, although I can start reading it more and more. But if you spend a bit of time, it's not so difficult. And they will explain you this, I think, right? Yeah, okay. You have more time? 3 minutes, okay. Now I want to come back. Assume you have executed this program and you've described this all concretely. Now I want to use this to get more structure on the unit group. This was my ultimate aim. Okay, now, then if you have executed that program, in some sense you have reduced many things to matrices over division rings, but where is my integral group ring? Imagine that I have executed this program and I described the rational group algebras as direct sums of this. Where the heck is my integral group ring gone? It's not so clear. Okay, so we have to do a bit more work. Now, luckily, in most cases, I don't have to know this explicitly for certain results. In most cases, and this is funny, if the matrices are of large degree, it's okay. So big matrices are okay. Small matrices are a disaster. And matrices over Z are complicated. 2 by 2 matrices over Z. Strange, eh? Explain that to your mother.
When you write this, it means that you already found the elementary matrices?
No, I haven't. But for nilpotent groups, if I remember well, we can do this. So 2 by 2 matrices over Z are complicated. 3 by 3 matrices over Z are easier for the things I want. But if you think geometrically, this makes sense. 2 by 2 matrices over Z, you think two-dimensional spaces. It's not a space over Z, but over Q it is. And you have less flexibility of moving around than in a 3 by 3 space. It comes down basically to that. So I want to explain what are the small components, and then I can continue with that tomorrow, tomorrow. Okay, so to do that, I have to explain you a notation. So this is section 4. It's again Weddertion Artin, but now other things. So I have to explain you what this is. There is a field. A and B are non-zero elements in the field. So it crosses the non-zero elements. And by this I know the quaternion algebra with parameters A and B. Quaternion algebra over F. What is this? It's the algebra generator over F by two simples I and J, but they satisfy the following relations. I squared is A, J squared is B, and Ij is minus Ji. So you can show that this is up to isomorphism F1 plus Fi plus Fj plus Fk with K equal to I times J. You know the classical quaternion algebra, this one you know. Classical quaternion algebra with the reals, you know. By the way, and I work with because I want -1 not to be equal to 1, so I work in characteristic, not 2. Otherwise, it's even commutative and funny. Okay. So this is a division ring. I always give as an exercise to my students in the second year course. Compare it with this. That's not a division ring. That's a matrix ring. Okay. But they are simple algebras with center F. Okay. I'm almost finished. There is a result that tells you when this is a division ring. Result in the sense you have to have solutions of an equation. What is it? ax squared plus by squared is equal to z squared. Something like Pythagoras, more or less. It's a norm. And if that has solutions or not, then it gives you a division ring or not. Now, what are the small components? We call them exceptional components. And I need that for tomorrow. Okay. So a finite dimensional simple rational algebra. So it's a simple algebra A that is an algebra over Q, and it's finite dimensional, and we call it exceptional. This is the word I'm defining. Well, there are two types, type 1, type 2. Type 2 is a non-commutative division algebra. Except a totally definite quaternion algebra. I'll do it over a number field because that's all you need. What is a totally definite quaternion algebra? It would mean that F is a totally real field and A and B are negatives. So for example, if F is Q, then A and B should be negative rationals. Okay. 2 is 2 by 2 matrices over Q, or 2 by 2 matrices over Q root negative D. And this is a square-free integer. A positive integer. You should exclude those. And the third one is 2 by 2 matrices of this form. 2 by 2 matrices over this where A and B are negative. You don't know why, but these are exceptional things. But you see, in some sense, they are small. 2 by 2 degrees over very small things. Now, what is so special about this field, and this field? I will define you tomorrow what is an order. There are finitely many units in the ring of integers here. And here there are finitely many units in an order in this thing, whatever that animal is now. For example, -1 over z has finitely many units. So exclude those small matrices over fields in which an order has finitely many units. These are complicated things, small but complicated. These things, this is a very big black box. If you have division algebras in QG, and you want to describe units in a large ring in there, in an order, this is a black box. Nobody has a clue. So for example, this is an exercise. You get another PhD thesis from me if you can do this. Describe me this group, the quaternion algebras of a ZC7. 7 because then this lives in a division ring, and we know nothing about this. I have to admit there's the results by Gabinebe. Gabinebe has an algorithm to compute finitely many generators of a large subgroup in any order in a finite dimensional rational algebra, semisimple algebra. If you apply, she's told me, she applies her method to this thing, the computer will never finish. It's too large. So it's possible to do theoretically. So when I say describe, of course, imagine you can do it for 7. My next question is replace 7 by something else. I want some kind of generic constructions that work in all those cases. And the sad thing is we don't know, apart from the bus units, we don't know of any other generic constructions. But we don't know how large the bus units produce something here. Okay, that's it for today.
Maybe we are running a